So, in this discussion we will consider vector modes and other material properties, material or waveguide properties. When we started the optical waveguide theory, we considered scalar modes. That is, we would like to quickly, we wanted to quickly get into the properties of optical waveguides, and so we took a scalar approach to simplify the mathematical complexity and so on. But actually, as we know, the light is an electromagnetic wave consisting of electric fields and magnetic fields and all its components Ex, Ey, Ez and Hx, Hy and Hz. So, if we want to have a complete picture of the light propagation in integrated optical circuits, we need to consider light as an electromagnetic wave, and we need to take what can be called as a vector approach, which considers all the components. So, before we proceed further, we will have to define what are modes. We have already seen in the scalar approach that a mode is a pattern of a field along with their propagation constant. We have mentioned that the modes, the mode field, this is the mode field and the propagation constant are obtained from the wave equation. We used a scalar wave equation and they are obtained as the eigenvalues and eigenfunctions of the scalar wave equation. In the same manner, we can consider the vector modes as the vector field components E and H along with the propagation constant. So, we need to have a composite vector field to define the vector modes. This is particularly important when we are looking at the vectorial properties of the waveguides and devices and want to manipulate the electric and magnetic fields and use all those effects. The starting point for this analysis is from Maxwell's equations. Maxwell's electromagnetic equations govern how electric and magnetic fields are related and interact with the medium. So, as we know, we have the Maxwell's equations in various forms. In the differential form, you can express Maxwell's equations as follows: del cross E equals dou B by dou T and del cross H equals dou D by dou T and del dot D equal to the charge density or equal to 0 if it is a uniform medium, and here also you have the current density which can be ignored if there are no free carrier currents, and also you have the magnetic field strength given to be equal to 0. These are 4 Maxwell's equations which will be useful to study the properties of light waves in integrated optical devices. And of course, we have ignored the charges and currents which can be incorporated if necessary to make the discussion complete. And also, as we know, and E and D fields and B and H fields are related through the constitutive relations as follows: D equals epsilon naught E, and if there are material properties, polarization of the medium can be included, otherwise it is not necessary. and you have the B given in terms of H as mu H, and these are the electric permittivity and magnetic permittivity of the medium in which the light is propagating. If the medium is uniform, this material constants, materials description, the parameters describing the material are constant, but as in the case of optical waveguides, if there is variation with respect to the fields, we have E and H to be functions of the point where we are observing the fields. So, they can be dependent on the space, also the propagation direction sometimes, and also with the time, they can be time varying also. So, we need to have a brief discussion about the nature of the materials that we use for integrated optics. So, we usually, when we study the electromagnetic phenomena in the medium, the first simplest medium that we can think of is a uniform medium, where we can express the electric fields and magnetic fields as simply the constants as simply epsilon naught multiplied by relative dielectric constant, or the magnetic permeability can be simply expressed as mu 0 into mu r. If the medium is non-magnetic, mu equals mu 0. So, this is a scalar, and we can also relate this epsilon r with the refractive index. As we know, the refractive index is defined in terms of the velocity of the light in the uniform space by velocity of light in the medium. So, we can say by considering the frequency and wavelength of operation, we can express n in terms of epsilon r as epsilon r is n square. Of course, it depends on the operating frequency, but at a given frequency we can express the relative dielectric constant in terms of the refractive index profile. So, if the media properties are varying with different points at various points, we can say that refractive index is a function of the medium point where we are observing, and like in the case of scattering problems, we have refractive index of the medium varying everywhere. So, we can also think of materials like this is a typical example for a material with uniform refractive index is the glass. And there are materials which have got non-uniform media. That means the properties of the medium varying with the different coordinates, and in particular as an example of non-uniform media, you can have a gradient index waveguide. So, let us distinguish media which is non-uniform. Non-uniform media has got epsilon varying with x, y, z, refractive index or the dielectric constant varies with x, y, z. Also, we have media which are called anisotropic, which means the properties of the medium depend on the direction in the crystal. So, in one particular direction you have one refractive index, and in the other direction you have another refractive index. Typically in the bulk crystals you call them as ordinary refractive index and extraordinary refractive index. Typical example of an anisotropic medium is a calcite crystal, where if you observe from a particular angle, it is possible for light to come in different directions, and you see what can be called as a double refraction. Double refraction is a manifestation of anisotropy of the medium. Similarly, you can also think of media whose properties can depend on the time. So, time dependent. Time dependent properties also are important. For example, in an electro-optic modulator, we would like to change the properties of medium with time. In that case, we need to use n as a function of time also. So, these are the various combinations or various material properties that we will come across. So, let us make a comment on the refractive index of the optical waveguides. Refractive index of optical waveguides we will make it more specific to optical waveguides. Optical waveguides are typically formed to have different refractive index in different regions, so that light is confined within particular regions. In the bulk optics, in the simplest cases, we know about total internal reflection, which is a means to explain light propagation in thick waveguides. Suppose you have a waveguide like this, which is quite thick, so that we need not use the wave optics. We can study these properties by considering light propagating at different angles in the waveguide. So, suppose you have the refractive index is n1 in the guiding region, n2 in the region outside, and if you launch the wave at a particular angle, it is possible for the light to refract at this point and refract at this point also, and beyond a certain critical angle it can reflect back to the same medium and get propagated. So, this geometrical distribution of light is useful to understand when the thickness of the waveguides is very large, and of course, when the dimensions become smaller and smaller of the orders of wavelength of light, the geometrical approach is not useful and we need to go to wave approach. And in the earlier discussions we have seen that we have used the scalar theory of the light propagation. So, now let us get back to the various refractive index configurations that are possible. So, two important refractive index configurations that we can identify are called the step refractive index, which we have considered in the last two discussions, and where the refractive index changes abruptly from one medium to the other medium. As a simple example, you can consider an optical waveguide where you coat a thin layer of another medium of a higher refractive index compared to the substrate to create, and above is the air. So, N1, N2 and N3, this is a substrate, this is the film and this is the air, and refractive index is constant in each of these regions. Such a refractive index variation of the waveguide is called the step refractive index, and the waveguides are called the step index waveguides, and we can express, we can plot the refractive index as a function of the distance. Let us say this is the x variation, we can say x as a function of the refractive index, as a function of the x the refractive index could be expressed. For example, if you have a refractive index of n1 at this point and n2 in the substrate and say n3 in the cover region. So, we have a refractive index profile which is like this. So, this is called a step refractive index. Similarly, when you diffuse impurities into the substrate to make the waveguides, we can obtain a refractive index which is gradually varying from the top surface to the bottom. So, we can express the refractive index variation as follows to draw it across. So, in the cover it is 8 again, and you have a refractive index n1 at the surface which is maximum, and towards the surface this n2 is the surface the substrate refractive index, and the refractive index changes gradually. So, this sort of profile is called a graded refractive index profile. So, mathematically, conceptually there is no difficulty with treating step index or graded index, but only thing is we should note that refractive index as a function of x will result in the wave equation and the differential equations with variable coefficients. differential equations with variable coefficients. So, we are talking about the step refractive index and graded refractive index. So, the graded refractive index could be of several types. For example, with the function that can be used to represent can be a linear function or parabolic or exponential or anything. It is possible to construct, it is necessary and possible to construct the refractive index profile as a function of x to use it in for very mathematical purposes. For example, we can fit a curve which is can be obtained by this function f of x can be obtained by the experimental measurements of the diffusion process. We can use a function of the form a into b, a plus b into f of x to determine what is a function of this. For example, f of x could be a function of x square. So, given a configuration or variation like this, we can find out the values of a and b to find out how the refractive index actually varies with the distance. So, you can have a linear variation of the refractive index f of x equal to say ax plus b. You can also have a parabolic refractive index variation or exponential and whatever way you like. And on the similar lines along the width direction also, if you have a channel waveguide, you have a refractive index variation that can be with the depth, and also you can also have a refractive index variation with the width. So, you can have a graded variation in both x as well as y directions. Suppose this is, you let me call it as a x direction and the depth is y direction. You can have a refractive index which is varying both x as well as y. And sometimes you can express for mathematical purposes that you can separate out the variables f of x into g of x. In particular, when you can express the refractive index as a sum of these variables x comma y is n square of x plus n square of y, or even n of x y n square x plus n plus y, because the squares of the refractive indices are entering into the wave equation. This is a more convenient form, and when we express the refractive indices like this, it is also possible to express the mode field profile in terms of the functions, variations along the x direction and variation along the y direction. This is popularly, this method of analysis in differential equation is popularly known as splitting the function into two variables, product of two functions, variation of parameters, or let us call it as variable separable. We need also make a note about the types of modes that can exist in optical waveguides. We have noted that most of the light has to be guided within the waveguide. If you have a waveguide like this, we would expect most of the light to be guided in this, and we have seen that the light could extend outside into the substrate and into the air. So, when the light is confined mostly to the guiding region, these can be called as guided modes or the waveguide modes, which consist of field in the core region, film region as well as the cladding region. The entire thing constitutes one mode and is characterized by this mode field and the propagation constant. Similarly, when the light leaks out of these optical waveguides, you can have what are called the radiation modes. Radiation modes are the modes which have got a field variation which is which represents the power leaking out of the optical waveguides. As a simple example, you have the oscillatory field within the guiding region and also an oscillatory field outside the guiding region. As we know that the light propagates as e power I beta z along the propagation direction, combining with the variation, the periodic variation along the z direction and periodic variation along the perpendicular direction, we can say that the light is propagating in this direction. The combination of wave vectors along the z direction and along the transverse direction could lead to a wave which is propagating at an angle. This can be used, this can be considered to be representing the radiation modes. Radiation modes are the modes which leak out of the optical waveguides. Several terminologies are used. For example, the radiation modes that leak into the substrate are called the substrate modes, which are confined to the cladding regions. If there is an additional cladding layer, the light could be confined to cladding regions. So, this can be called as a cladding modes and so on and so forth. Finally, we would like to do a simple exercise to relate the vector modes with the scalar modes. We have noted that Maxwell's equations represent the entire set of electric and magnetic fields of a light wave. So, it is possible, it is known and possible that by manipulating the Maxwell's equations we can derive what can be called as a wave equation. Let us quickly revisit the derivation of the wave equation to bring out an important difference of the modes of an optical waveguides. So, let us consider starting from del cross E equals minus dou B by dou T and del cross H as dou D by dou T, and the dot products del cross D equal to 0 and del cross B del dot B equal to 0. So, I am considering a uniform medium, and of course, the time variation also could be reduced by taking e power I omega t as the time variation of the field, which implies that we are doing a Fourier analysis. So, all the electromagnetic fields are replaced by the Fourier coefficients. So, this B will be replaced by B x comma y comma z multiplied by e power I omega t. So, the variations with respect to omega could be relieved by replacing the B with B omega. So, this results in fields which are in the time variation there will be I omega multiplied by B. So, for simplicity we do not use we use the same notation and replace B with I omega B. So, I omega t and I omega d, I omega b and I omega d. So, this implies all the fields including the right side, because there is no time variation here. We can say that these represent time varying fields or the harmonic fields. The fields are harmonic. So, in order to get the vector wave equation, let us take the curl of the first equation and expand. So, minus I omega into del cross B. By using constitutive relations we can replace B and D. D equal to epsilon E and B equal to mu H. So, minus I omega into del cross mu H. So, minus I omega mu, assuming this is non-magnetic medium, I can remove out, and the magnetic variation magnetic field medium properties are constant, we can remove the mu and replace with a del cross H. So, this can be replaced by the curl theorem by using del square E plus del dot E or del cross E, okay, del of del cross E. So, del square E plus del of del dot E minus del cross H. So, we can replace del cross H with this expression to obtain minus I omega square mu, and I will use this to replace me with E. So, we have only the electric field in this expression. So, the entire, of course, we have made a few assumptions that the medium is uniform and the electric field is not coupled to the magnetic field. We can say that, of course, this we can further simplify by using this equation. For example, I can do del dot D can be replaced with del dot epsilon E, and of course, now if the epsilon is a constant, the medium properties are constant, we can remove out of the epsilon sign, but as you know, for the graded index waveguides and many problems, epsilon is not a constant, and so we cannot remove, and we will just replace as using the product rule, we can replace this expression del dot E multiplied by epsilon plus E dot del epsilon. We do not need to put a bracket anyway. So, we can use E equals 0 according to the Maxwell's equation. So, we can say that del dot E equals E dot del epsilon by epsilon with minus sign. So, I can replace del square E, this one becomes minus. I can also replace this with I square is there here, where is that? I square, we have one more I square here. So, this becomes minus 1, and so entire thing is 1, and we can replace this entire thing with omega square mu epsilon by noting down that the velocity is a function of the frequency and wavelength. We can replace this with omega square epsilon E, and also we will note epsilon is epsilon 0 into n square. So, omega square mu epsilon 0 into n square. So, this entire thing could be replaced with k 0 square, where if you say this epsilon mu is the velocity is 1 by mu epsilon 0, we can get this is equivalent to 2 pi by lambda. This entire thing is equal to 2 pi by lambda or k 0. So, this becomes just k 0 square n square multiplied by E. So, I will replace this here, and minus sign is there here. So, this becomes plus, or there is a minus sign here and minus sign here, there is a plus sign here. So, by proper manipulation, please check, plus k 0 square n square of E on this side, and this we need to put to the other side, and because of already minus we have used up, when it goes to that side, del of del dot E, and we have replaced it with E dot, see when we make it equal to 0, we have got del dot E equals minus E dot del epsilon by epsilon, and of course we have one more del. So, we have considered the wave equations which are of the form del square of E plus k 0 square n square of E equal to 0 in a uniform medium. We would like to note that if the medium is not uniform, on the right hand side we have a factor which is depending on del epsilon by epsilon. This is an important feature of which will be useful for integrated optical waveguides dealing with graded index waveguides. We have a simplification when for the step index media by using the boundary conditions. Because each of the regions is uniform, we can assume we can use this wave equation for each of the regions and then match the boundaries. That is what we have done in the scalar approach. But when we would like to take the vector approach, we cannot do that, and we can say that the mode fields are coupled. For example, Ex, Ey, Ez are interrelated by this expression. And if you do a similar exercise with the del cross H, we will observe that it is possible to note that E and H fields also are interrelated. Depending on the medium properties, E and H fields are interrelated, and we get fully coupled set of equations. That means there are 6 equations. This is equivalent to 3 wave equations, and similarly we have 3 wave equations with respect to H. So, all the 6 could be coupled due to the factors like this. This is an important feature that we should note, which is not existing for the uniform medium. So, finally, we would like to do a small exercise where we can separate out the mode fields of a slab waveguide by starting with the Maxwell's equations for a slab waveguide. We can separate out the vector modes into TE modes and TM modes. So, this is a slab waveguide. So, that to bring out the vectorial nature of the modes of an optical waveguide, we can use the example of a slab waveguide and note how TE and TM mode fields are represented, which components of electric and magnetic fields exist for TE modes, which components for TM modes can be obtained in a very simple manner, once again starting from the Maxwell's equations. I will once again use del cross E equals minus dou B by dou T and del cross H equals dou D by dou T minus dou B by, and we will replace with the Fourier time harmonic fields minus mu into del H by del T, and del cross H also replace with, so that we have only E and H fields, epsilon into dE by dt. Quickly let us expand the fields using the matrix approach. We can write del cross E as the matrix form by using the x component, y component unit vector and z component unit vector into d by dx, d by dy and d by dz, and Ex, Ey and Ez. This is how we can evaluate del cross E, and we get x into x component into dEz by dy minus dEy by dz. Similarly, plus or minus y component into y component d by dEz by dx minus dEx by d by dx and dx by dz plus z component dEy by dx minus dex by dy, and this has to be equated to minus mu into, of course now there is no cross, we can simply say x component into dhx by dt mu is outside anyway, plus unit vector in y into dhy by dt plus unit vector on z into dhz by dt. So, we can equate the x components, y components and z components separately, and similarly the same exercise for del cross H. Using matrix we can write it without doing, by looking at the symmetry and replacing with electric fields with the magnetic fields. And of course, we have on the right hand side there is a positive sign, and we can express it quickly as del Hz by del y minus del Hy by del z, and y component del Hz by del x minus del Hx by del z plus z component into del H not E Hy by del x minus del Ex by del y, which is equal to epsilon into x component into d Ex by dz and y component dy by hy by dt, this is t not z, minus, to distinguish I am putting this z plus z component into dh by. So, now we can equate x and z components and then express. Before that we will make a simplification saying that the field is only varying along the x direction and the propagation is along the z direction, and time variation is taken as e power I omega t. With this simplification we can reduce all these fields into 2. So, when we replace, because the field is not varying along the y direction, we can say that dy components do not exist, and so we can replace these fields. For example, x component dz by dy is 0 because y variation we are not doing, and we can z variation we can replace with I beta into E by e power I beta z, I omega t minus beta z, I omega t is time variation, e power minus I beta z is the z variation, we can say minus I beta, and similarly Ex also can be replaced with e power I beta z x component and y component here, and here also y component can be deleted. Similarly, all the time components can be replaced with I omega variation, I omega hy and I omega hz. Similarly, here also I omega Ex, Ey and Ez. So, we will try to equate now. So, z components we need to kill, x components, this x component also goes and this x component also goes, and the second one is xz, third one is hz. So, by now properly equating we get minus I beta Ey equals I omega h y. Is it so? No. I omega hx, x component of Ey related to h component of hx, time variation. So, okay, let us quickly write, then we will go back. I beta Ey, or I will delete something so that we can make use of this space. So, we will write for the one set of fields and replace it with other set of fields for ease of operations. For example, we have I beta Ey equals minus mu I omega hx. This is one equation we have from the other one, and for y minus E z by Ex minus or minus plus I beta Ex should be equated to the y component here. I omega minus mu I minus mu omega I mu omega h y. This is the another equation, and for the other one E y by Ex, Ey by Ex z component should be equal to minus mu I omega h set. These are the three equations that we get from the first set of equations. Similarly, we can get from the second set also. We can write without looking at it, minus, see, instead of mu we get epsilon, that is the main difference, and minus goes minus I beta into hy. I will use a different color, so that I will use a blue color, so that minus I beta into hy equals minus instead of mu epsilon plus and I omega Ex. Similarly, that is minus is already there, and minus or minus plus we have made it, yes, minus del hz by dx minus, with respect to z, minus I beta plus I beta into hx equals epsilon into I omega hy. Ey. And finally, one more, dhx, or which is z component hy by dx equals epsilon I omega Ex, epsilon I omega epsilon Ez. So, these are the two distinct sets of equations. If we, I think we will erase so that we can use this properly. So, let us look at the equations and look at the overall picture of what is happening with x, y, z components of electric and magnetic fields. So, this equation represents a relation between Ey and Hx, and this equation has got a derivative with respect to x, that is the important part. So, we can replace the, say for example, if you want to have only one particular components, we can replace with Ez, and Ey with respect to x is also there here. So, we can eliminate, say let us try to eliminate Hy. So, Hy can be eliminated by using this expression. So, let us combine these equations, dEz by dx plus I beta into Ex equals minus I mu omega into Hy can be combined with this thing by to replace get to Ez. And if we note carefully, we will see that Ey component is related to Hx component and Ey component is related to Hz component also. So, this is a group. Ey component is related to Hx and Hy, this equation, and Ey component to Hz, Hx and Hz. Similarly, Hx component can be related to Ex component and Ez component. So, the conclusion is that we can group the fields in terms of Ey, Hx, Hz, and Hx is Ex, just a minute please, Hy component in terms of Ex, Ez. So, these are the equations could be split up distinctively into two groups, one containing Ey, Hx, Hz and other containing Hy, Hx, Hz. If you look at the geometry that we have, and if we say that the propagation direction is z, we can say that the fields which are, and this is the x direction, you have the Ey field is in this direction and there is no Ez component. So, these could be called as TE modes. So, TE modes have got field component along the plane of the waveguide. Similarly, if you look at the other equations, we can say that the Hy component, or the usually we describe the polarization states or the modes with respect to the electric fields. So, you have an electric field along the, this is x direction along the x direction, and this is the propagation direction. Ez component is also there, but Hy is in the plane of the waveguide. So, this, and there is no Hz component. So, we can call these as TM modes. We can have TE modes having Ey, Hx, Hz, and TM modes having Hy, Ez, Ex, and we can use the other relationship to eliminate the other variables. For example, Hz variation is there here and you can replace with Hz variation. So, you have del square Ey by dx square related to, once again Ey is there here. So, you can you may be able to get Ey, and if you replace with Hz, you can get omega square mu epsilon into Ey. You get the differential equations for only for Ey. So, in the case of the TE modes, we can get d square Ey by dx square plus omega square mu epsilon to Ey. This we can replace with k0 square n square and E y component. And similarly, for the TM modes, we can replace with del square Hy by del x square plus k0 square n square of Hy equal to 0. So, one important feature that we observe here is that we have the scalar wave equation, except that psi is replaced by Ey, and in this case we have the same form of the equations that we used for scalar approach, where psi is replaced with Hy. So, by properly interpreting the wave function psi, we can use the same scalar theory that we described earlier for TE modes as well as TM modes, by properly noting which are the components existing. One more important point to be noted is the boundary conditions. Boundary conditions are expressed in terms of the tangential components of the electric field and normal components of the magnetic field. So, we need to use ET1 equals ET2, where T1 and T2 are the fields in the film region and the guiding region. So, in this case the Ey is tangential. So, we can directly equate Ey1 with Ey2, which is exactly same as the scalar approach that we have taken without mentioning about the electric and magnetic fields. In the case of TM modes, the electric field is not at the boundary the electric field is not continuous. We do not have a field which is just along the boundary, but you have a magnetic field which is tangential component. So, HT1 should be equal to HT2. So, H components in the TM mode can be replaced with E components, and so you have, for example, if you observe it at this point, you have N1 HT1, where is that HY, this is the component HY. You have the HY component here expressed in terms of EX component. So, the boundary condition reduces to N1 square ET1 or X1 to N2 square Ex2. So, by modifying the boundary condition to include the refractive index on both sides, we can use the same approach that we have taken for scalar mode, except that the boundary conditions are different. So, this leads to a slightly more improved form of the dispersion equation for TM modes. So, the beta is different, and so the VB curve or all the values are slightly shifted for TM modes. If this is for the TE modes, this one can be for TM modes. So, the dispersion curve for the TM modes is slightly shifted compared to the TE modes. So, this is a typical, of course, in the case of more complicated waveguides, the mathematics could be complicated, but it is the scalar approach that we have taken is quite useful to study the vector modes, particularly when there is no coupling between the fields. So, thank you very much.